Hello, good morning, everybody. Hey, welcome to Papa Lim Physics Classroom. Today we'll be going through one prelim paper, SJI 2022. Okay, same as before, in this video I'll be going through the questions in the entire paper too. So it will be a long video. So for those who have actually got the paper and you want to check out certain questions in mind that you have some misconception or certain doubts, okay, just feel free to scroll to the particular section of the video that you are interested in. Okay, if not, for those who want to try the paper, I left the soft copy in my Google Drive. You feel free to go and access the Google Drive and download the paper and try. Okay, because this paper is actually quite a good paper. It got some interesting questions that I think that all students should be aware of it. Okay, now, without delaying, okay, I will go through the paper now. For this paper, I have actually I already highlighted some of the interesting questions that you may want to take a look. Okay, so in this paper, there are like a few sets of questions that you might be interested in. Now let's look at your question 1. Now, question 1 here, you have a particular rocket, okay, SpaceX, okay, landing on a planet Y. Okay, take note, this is planet Y, not our usual Earth, or whereby you have the gravitational field strength is G is 10 Newton per kg. Now, take note is what we are looking at for part 1 is we are looking at the weight of the planet X. And weight of the planet X, we know that the formula for weight is weight equal to mg. So we are given the mass, okay, okay, here the mass is 1.8 times 10 power 6 kg, but we do not have the gravitational field strength. Okay, we do not. Okay, take note, this is planet Y, so the gravitational field strength is not 10 Newton per kg. Okay, so the first task that we need to do is we actually need to find the gravitational field strength. And in this case, we are given the speed time graph, and gravitational field strength sometimes is also known as the acceleration due to free fall. So what we are looking at is, if I want the acceleration from a speed time graph, I am looking at the gradient of the speed time graph. And in this case, I'm experiencing a free fall at the first 8 seconds. Okay, like what I mentioned to the in the question. Okay, free fall in the first 8 seconds. So which means the gradient in the first 8 seconds will actually give me the acceleration. So which is why you look at the workings at the beginning, I'm actually looking for the acceleration for the first 8 seconds. Okay, v minus u divided by delta t. And from here, you give us an acceleration, which is 9 meters per second squared. In this case, this acceleration is the acceleration due to free fall, okay, or sometimes what we know as the gravitational field strength under 9 Newton per kg. Okay, so once you have the acceleration for the first 8 seconds, I actually got the gravitational field strength. So what I do is I just substitute the acceleration, okay, into the formula weight equal to mg, and I will actually have the weight of the SpaceX. Okay, so just take note for this question here. I think the tricky part here, or the things to take note, is that the gravitational field strength is actually not 10 Newton per kg. So students will have to take one more step, okay, to actually locate or to identify the gravitational field strength for this particular planet Y. Now, for part B here is you're asked to draw the free body diagram for SpaceX during the descent. Okay, and one of the obvious things that we all know, since the mass is given, there is definitely weights in the SpaceX that we are looking at. So weight is pointing downwards, and the thrust is actually given by the rocket. Okay, so the thrust would be to slow down the rocket when it's descending. So the thrust will be pointing outwards. Okay, so in this case, okay, I would say that these two forces are what we call the standard pair of forces that we always see in the free body diagram. Now, what is interesting here is calculate the magnitude of the thrust here. Now, based on the question here is that the object is actually descending. Okay, so after 8 seconds, okay, the object is actually descending, so it's actually going downwards. So what I do is since the object or the motion of the object is going downwards, I like to take downwards as positive. Now, under the downward as positive, the forces acting on the object due to the free body diagram, there's only two forces, which is T and W. So what we usually do is, given that downwards is positive, okay, so I would like to use Newton's law, which is F net equal to ma. So downwards is positive, so the forces I'm looking at is W minus T. Okay, then after that, by the acceleration. Now, things to take note is for the acceleration, okay, we are looking at the time after 8 seconds. So which means now I'm looking at this area, this curve here. Okay, so in this velocity time graph, okay, if I want to find the acceleration for this section of the graph, I am also looking at the gradient of the line here. Okay, so I'll repeat the same thing. I'll look at the gradient. I'll be using the formula final minus initial divided by time taken. But it's just that now I'm looking at the right side of the curve here. Now, so what we are looking here is that for the second part here, okay, the acceleration, this is the mass. The acceleration is given by the graph, which is the final speed of the object is actually 0 meter per second. Okay, because it's actually stopped, it landed on the object, landed on the planet, and the initial speed is given by 82. Okay, it's by 82 meter per second. And what's the time taken? And based on the time taken by the graph is after 8 seconds, it lands on planet X at 28 seconds. So which means that there's a difference of 20 seconds. Okay, so this will be the acceleration of the SpaceX itself. Take note that this particular number here is actually a deceleration. So this number is actually a negative number. Okay, and if you work out the number, you'll find that the acceleration in this case, which happens to be a deceleration, is actually negative 4.1 meter per second square. Okay, so weight you are given in this question here, your weight is given, you found in part A, which happens to be 1.6 times 10 to the power of 7. Okay, 1.6 times 10 to the power of 7 minus T. Okay, and you do your algebra, you'll find that T, the answer given here for T will be 2.36. 2.36 times 10 to the power of 7 Newton. Okay, so this will be the answer for the upthrust. Now, for this question here, just take note that the acceleration here is negative sign because it is a deceleration based on the graph that's given. Okay, not positive number. Now, for part 2 here, in reality, you'll find that as I keep burning the fuel, okay, the weight of the object is actually decreasing. So if you look at Newton's law, which is the weight minus T, okay, this is F net, what we mentioned in the beginning. Okay, so this is, in this case, you'll find that, okay, the weight in real life, the weight is actually decreasing. But my upthrust, the thrust given by the rocket, is actually maintaining. Okay, I maintain my T to be the same number, to the same value. So my thrust is actually constant. So you'll find that because my weight is decreasing, my thrust is constant. You'll find that the net resultant force acting on the object is actually increasing. So which means that the object or the space shuttle itself will actually be experiencing, okay, acceleration, increase in your deceleration, aka being the number will be getting a bigger negative number, or what we know as an increase in your deceleration. Okay, so this is one of the classic, one of the assumptions that we like to make during our calculation for ease of calculation. Okay, is that the mass of the object, the mass of the space itself is actually constant. But in real life, it doesn't happen. Okay, so just take note of this. Okay, so even in I would say on road, when we look at force driving, engine forces, all these things, we tend to take it that the mass of the car or the object is actually fixed. But in real life, as I burn more fuel, my mass of the car, the weight of the car actually will be decreasing. So if I maintain the same engine force, it actually, with the same thrust or with the same engine force, you'll find that the car actually accelerates better, faster and faster, because the weight of the car is actually getting smaller and smaller. Okay, so just take note of these slight assumptions or this particular answer. Now for question 2 here, we actually have a velocity time graph again, but now we are looking at two particular objects. We have the hot air balloon and we have the ping pong ball. Okay, now the ping pong ball was released, okay, at 2 meters per second. Now what happened here? Okay, the question asks, acceleration of the ball is maximum at its height. Definitely. Okay, because when the ping pong ball is dropped, okay, when the ping pong ball is dropped at the beginning, okay, the ping pong ball is dropped, okay, the forces, the speed of the ping pong ball is actually negligible in this sense, okay, because it's not moving at all. Okay, because the moment I drop, okay, that particular instance is actually momentarily at rest, and because the speed is negligible, you'll find that the air resistance is negligible. Okay, here students, you have to take note, is every time when we deal with air resistance, I always caution or I always remind the students to actually take note of the fact that air resistance and speed are actually related. The faster you move, okay, the bigger is your air resistance. So now in this case, you will have not moving, you're negligible speed or you're momentarily at rest. You'll find that my acceleration will actually be 0 now. And you'll find that the weight or the force that's acting on it is actually the weight. And when the only force you act on it is weight, you'll find that the acceleration experienced by the object itself will be known as your acceleration due to gravity, or your acceleration due to free fall, which is 10 meters per second square. So during that instance, you will find that the acceleration for the object is actually the highest. And how high is it? It's actually 10 meters per second square. Okay, so this is one of the common characteristics we have when we're dealing with free fall. Free fall, although we have the notion that if in the presence of air resistance, my acceleration of the object tend to decrease. But the decrement is not immediate. The decrement actually starts after a short interval, when the speed of the ball is actually of a certain value whereby the air resistance is no longer negligible. Only that instance onward, then with the impact of air resistance in play, you'll find that the acceleration of the object will start to decrease. And so decrease from where? From 10 meters per second square, which is your acceleration due to gravity. Okay, so now part 2 mentioned that how is the change, okay? Describe the change, okay, until it reaches terminal velocity. Like what I mentioned, okay, based on the graph, okay, we are looking at the gradient of the graph, which because this is velocity time graph, where the gradient of the velocity time graph will actually dictates the acceleration. So you'll find that the gradient of the line is actually getting gentler and gentler, and eventually it reaches become a horizontal plateau line. Okay, so which means that it will tell us that the gradient of the line is actually decreasing. Okay, until it becomes plateau, whereby the gradient is actually 0. And since we know that gradient is actually acceleration, you'll find that what this implies that as gradient decreases, it also implies the acceleration of the object is also decreasing. And when the gradient of the line becomes 0, it also implies that the acceleration of the object is also 0 meters per second square. Okay, so in this case, you'll find that the gradient actually depicts what actually happens to the acceleration. Okay, and in this case, it's actually decreasing, and eventually it hits 0. And when it hits 0, the gradient is 0, or what I call acceleration is 0. You'll find that this particular number, okay, is actually implies what we know as your maximum speed. Okay, and this is what we call your the maximum velocity, and this is what we call your terminal velocity. Okay, so the object from this point onwards at 2.2 seconds, it will actually be falling at a constant velocity. Okay, and what we know as your acceleration equal to 0. Okay, now calculate the average velocity of the hot air balloon. It's hot air balloon. Okay, not ping pong ball. Now, average velocity, like we mentioned, okay, average velocity, look at total displacement divided by your total time. So in this case, remember, for kinematics graph, when we're looking at total displacement, okay, total displacement is actually another way of looking at total displacement is actually area under the graph. Okay, the area that we are looking under the graph. Between where? Between 0 to 3 seconds. So now between 0 to 3 seconds, the area under the graph, which is this gigantic, not triangle, is a trapezium. Okay, so this area here, okay, is the displacement of the hot air balloon. Okay, area under the graph is displacement. So aka, you need the area first, divided by the time, which is 3 seconds, which is what the formula actually trying to tell us. Okay, I need to find the area of the trapezium first. Okay, then after that, time is 3 seconds. I will get the answer to be 5 meters per second. Okay, take note, answer has to be 2 SF, 2 or 3 SF. Okay, plus unit. Part 3 deal with pressure, combustion engine. Okay. Now, for question 3. Now, we have question 3 here. Question 3 deals with pressure. Now, one thing about this question here, I would say the important things after reading the whole stem or the whole story is that, in this particular section, is that the pressure of the air flowing through the section pipe decreases as the diameter decreases at x. So this statement is actually trying to tell you that the pressure at x is actually smaller, it's actually lower because of the speed. In this case, it's because what happened is that at x, the speed of the air particle at x is actually very fast because of the small area here. And the small diameter means the speed passing through x is actually very small. And so when the speed of x is actually very small, you'll find that the particle at x is actually slightly lesser than other components, other locations. And because the amount of particle at x is lesser, the force exerted will be lesser, and as a result, with per unit area, you'll find that the pressure at X actually would be slightly lower than the rest. And because of the slightly less amount of particle at X, you'll find that the pressure X actually decreases quite significantly when the speed increases. Now, for second question here, we're looking at is the barometer. Now, for barometer picture here, I would say that the common thing that we're looking at is at the surface of the barometer. At the surface of barometer is what we call your atmospheric pressure. Okay, in this case, I think it's not anything hidden. It's a common thing that we look at for barometer. We actually looking at atmospheric pressure, and atmospheric pressure is always at the surface of the barometer here. Now, after looking at question 3, okay, so now we are ready to start question 3. Now, question 3 mentioned that how the air pressure in X decreases with the diameter of the pipe here. Now, so what we are looking here is to explain that particular phenomenon I mentioned previously. But pay attention to the fact that the question asks, how does figure 3.1 shows? How does figure 3.1 show? Now, what we are looking here is this. When we refer to figure 3.1, how do I know that this section here is a lower pressure? Okay, other than the fact the question told me about it, how does figure 3.1 represent it? Okay, so this is your P atmospheric pressure. This area is a P atmospheric pressure. Now, how does this picture depict that the pressure is actually lower? Okay, it's by the fact that the water column here, the water column is actually higher than the rest. Okay, so this additional water level means what? It means actually there is a difference in pressure. So which means that the atmospheric pressure is actually larger than the pressure at X. And because there's a temperature difference, you'll find that the force will actually push the water level up. And that's how we know that because of the additional in water level, slightly higher heights in the water level, this will actually tell us that the pressure X is actually lower than the atmospheric pressure. Okay, because the water level has actually been shot up. Okay, and this is what you need to tell this marker is that because of the height, the fact that the height of fuel is higher than the tank, this will tell us that the pressure is actually low at X is actually lower than the pressure in the tank. The difference in pressure, remember, the difference in pressure gives rise to the force. Now, for part B1. Now, for B part 1, we look at atmospheric pressure. Now, the question hinted us is to use figure 3.2. Now, figure 3.2 atmospheric pressure, I would say this is the standard operation whereby students, you should know how to read and how to use the barometer. So this is 76 mm. And you're given the density and you're given the density of the mercury. Remember, in this case here, we are looking at mercury. So the density that we are using should be density of the mercury. Okay, formula H rho G, again, nothing fanciful. Okay, so the height, remember when we have the height with 760 mm, so you need to change this to meter. So the unit for this height has to be meter, SI unit. And everything is SI unit. This is the mercury, density of the mercury. Okay, so with everything in play, you just use your calculator, you should be able to get the answer out straight away. Now, determine the gas pressure at X. Okay, gas pressure at X, same thing. Okay, now gas pressure at X, this figure 3.1. Okay, now let's take a look. Gas pressure. Now, the gas pressure that we are looking at will be the pressure. This is the pressure, atmospheric pressure. Okay, so remember, if you have the same fluid, same planet, and same height, you'll find that this area will actually have the same pressure. Okay, so this is what we mean by atmospheric pressure. Okay, so this area are atmospheric pressure. So atmospheric pressure, remember, one of the key tricks about atmospheric pressure is, remember, the pressure actually comes from everything and anything above you, So which means this atmospheric pressure, this pressure is actually contributed by this amount of height. Okay, plus above this height of the fluid, you actually have X here. So this actually would be your pressure X, okay, at the top of the fluid here. So which means that at at atmospheric pressure here, okay, at this green color area, okay, atmospheric pressure actually due to where? Atmospheric pressure is due to the pressure from the fuel, and the pressure due to X. So these two components will add up to be your atmospheric pressure. So in a nutshell, you'll find that actually your atmospheric pressure is actually consists of the pressure at the fuel itself plus the pressure at X, okay, which is what we call your gas, okay. So this, I will use it for gas at X, okay. So which means if you rearrange, you will find that the gas, okay, will be your pressure of the fuel. And how long is the fuel? Remember, fuel, we are looking at a height of 32, okay. Then after you have a height of 3 cm here. Okay, so the fuel that we are looking at here would be easily, okay, the difference between them, this will be 32 minus 3 cm, which is 29 cm. Okay, so 29 cm is the height that we are looking at. So what we are looking at, so that's why I have a 29 cm here, which is, remember, SI unit is meter. Okay, followed by your G, and this will be the raw density of the fuel itself, which is 850 kg per meter cube. Okay, remember SI unit for height. You have height 29 cm, you must change it to meter. Atmospheric pressure, you got it in the at part 1. Okay, so once you substitute all the number, you should be able to get the pressure X, pressure gas or pressure X to be 101 kilopascal. Okay, so that will be the answer for this particular section here. Okay, state how the pressure difference. Okay, how the combustion engine made use of pressure difference to mix the fuel and air. So now what happened here is, remember, the pressure that we are looking at, or how does the engine works, it relies on the fact that there's a small pressure, there's slightly lower pressure at X. Okay, this is lower than the atmospheric pressure. So what it does is, with the increase in air molecules, if my air is actually coming in at a high speed, if my air is coming in at a high speed, okay, you'll find that the more air I flow through, you'll find that the speed will be faster and the pressure X will be lower. So the bigger the difference in pressure, more fuel will be pushed upwards. Okay, more pressure will be pushed upwards. Okay, and when the fuel is being pushed upwards, the fuel and air will be mixed, will mix together at the opening here, X. So that's what your combustion engine does. Okay, by controlling the amount of air intake, I can actually regulate the fuel intake also. So the air intake and the fuel intake, they are actually linked together because of the difference in pressure. So that's what you are trying to, you need to tell the marker about. So which means that the pressure, they will have a lower pressure, okay, or the difference in the two pressure, you'll find that you will actually set up the upward force, okay, to push the fuel up, okay, to push the fuel up the nozzle. So when I push the fuel up the horizontal section, you will find that the air and the fuel will be mixed together. Okay, so that's how your combustion engine mix fuel and air together. Okay, so that's how the combustion engine works. And get a simplified version of it. So by taking it, so here what we are looking at here is that we make use of the difference in pressure. Okay, and the difference in pressure give rise to an outward force to push the fuel upwards, okay, and causing it to rise up and thus mixing air and fuel together. Okay, so this is how we use the questions, how we use the information given in the question to help us answer the questions that is required. Now for question 4 here, question 4, we have a freezing. Okay, we have an ice freeze. Okay, it takes 20 minutes for the tray to drop to its freezing point. For the tray to drop to freezing point. Now calculate the rate of flow. Okay, calculate the here what we are looking at is calculate the heat loss by water and ice cube as it cool down from 31 degrees Celsius. Now when I'm looking at cooling down, there are actually two sections here. Okay, so I need to cool down the water first. So which means the water and the ice cube tray, there are two components that we're looking at. We are looking at the water and we are looking at the ice cube tray. So in this case here, we are looking at water first. So let's say if for water, okay, the water is 31 degrees. So if you look at the cooling curve for water, this is the temperature. Okay, so at 31 degrees, okay, the still water is cooling down okay, until it hits 0 degrees Celsius. Now at 0 degrees Celsius, you'll find that for water, okay, it's still water. It has not reached its freezing point yet. It has not started to freeze, but it reaches its freezing point, which is 0 degrees Celsius, okay, for water. And similarly for the ice cube, okay, similarly for an ice cube. So let's say I use a different color. So water is red. So let's say for ice cube is blue color. So for ice cube, same thing. Okay, ice cube. Okay, ice cube is also at 31. Ice cube trace at 31 degree. He will reach the temperature 0 degrees Celsius. Okay, so the ice tray will reach his 0 degrees Celsius. So which means there will be cooling. So it will still be a cooling down phase. So a cooling down phase here, what we're looking at is for your water. For your water, okay, at 31 to 0 degrees Celsius, we are looking at your cooling phase, which is your MC delta theta. But in this case, we are looking at water. So this is your water. This is your water. Okay, so your mass will be the mass of water, which is 0.2 kg. The heat capacity will be heat capacity of your water, which is 4,200 joules per kg per Kelvin. And what's the change in temperature? Remember, you are only looking at the water cooling down to 0 degrees. Okay, he has not started freezing, it has reached its freezing point only. So that's why the change in temperature is 31 degrees Celsius, okay, which is 31 degree minus 0 degrees Celsius. This is for water. Now, for the ice tray, okay, you can use MC delta theta, but the information given to us is in terms of heat capacity. Okay, so the formula that we're looking for will be heat capacity C delta theta. Okay, heat capacity of the change in temperature is 31 degrees Celsius. Change in temperature from 31 degrees Celsius to 0 degrees Celsius. Okay, so once you put in your value, okay, you'll find that, okay, you will actually have derived at the answer of 224.8 watts here. Now, one thing to caution students is that the important thing is that we are dealing with that there are two particular areas, there are two particular sections you are looking at. One is the water, and the other one is ice cube. So you must look at both sections here, the water and the ice cube. And at the same time, both items actually go through the same processes, which is 20 minutes. Okay, so in the calculations, okay, in doing the calculation, students, you have to take note, you need to input two components. And the second booby trap that you must remember is that the time taken is 20 minutes. So in this formula, you have to convert it to seconds first. It has to be SI unit. So remember to convert it from 20 minutes, convert it to seconds first. Okay, the 1,200 seconds has to be included in the formula, not 20 minutes. Now, part B here now is this. Calculate additional time needed for the ice in the ice cube to be completely frozen. Now, for the ice to freeze, okay, completely frozen. So which means that your ice cube now doesn't stop here. Okay, so this is your water. So for the water to freeze, I must start my freezing, okay, until 0 degrees Celsius. So which means that I have to look at the latent heat of fusion. I have to include the latent heat of fusion in the calculation now. And this is the additional time or additional energy I need, okay, for me to freeze. Okay, so now in this section here, okay, you'll find that the time taken, the energy needed is actually the energy, or the extra energy I need is actually the time taken for me to freeze. Okay, so I need to factor in the latent heat of fusion. So which means energy, the other formula I'm looking at is power times time equal to energy mass times latent heat of fusion. So this is the time that I'm supposed to calculate. Power, I have the power already. Power, I calculate part A already, which is 24.8. Mass, I also know is 0.2 kg. And the latent heat of fusion, which is given also in the question at the top there, okay. The latent heat of fusion is actually 330,000 joules per kg. So once you substitute into the formula, you'll find that the time taken will be 2,661 seconds, or what we call 44 minutes. So this is the additional time I need. Okay, other than the 20 minutes of freezing, 20 minutes of cooling down to 0 degrees Celsius, I need another 44 minutes for the water to freeze into the ice. So this is the additional timing that I'm looking at. Okay, so just take note of this. So remember, in this section, part A and part B, it actually breaks down the freezing into two different sections. The first section we are looking at is the cooling down. This section here is the cooling down. Okay, so this section is the cooling down. Part B, look at the freezing. Okay, part B, look at the freezing. Okay, so there are two sections in this question here. Now for part C here, okay, part C, you will find in reality it takes a longer time to for it to freeze. Okay, the time taken to freeze is longer, definitely. Okay, why? It's partly also because the assumption that we make in the calculation A and B, we have not factored in the energy loss to the environment. Okay, so which means other than the ice cube losing energy to freeze, okay, it actually in real life it actually have losses. Energy will also be lost, okay, from the tray to the environment itself. So which means the energy while I completely cool down from initial temperature from 31 degrees Celsius, okay, I take 20 minutes. But in real life is that the energy taken, okay, to cool down is not solely just for cooling down. I also lose energy to environments. I also lose energy to trade. Okay, so these different platform or these different avenues, okay, will actually affect the time taken for me to freeze. Okay, so that's why you'll find that the difference in temperature, okay, blah, 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 blah. Now, part C deal with the fact that the fact that the timing to freeze is actually longer than 20 minutes. This one, in real life, this is actually what happens. Because in the calculation for A and B, we actually look at the heat loss due to freezing at a constant rate. But truth be told is that in real life, you'll find that as my temperature decreases, the rate of heat loss, the rate of freezing, okay, the rate of cooling down actually decreases. It's not a constant rate one. Because as my temperature difference between the environment decreases, okay, as my temperature drops nearer and nearer to the room temperature or to the room temperature, you'll find that, okay, the rate of heat loss actually decreases. It's not a constant rate. But what I did in part A and part B is I assume that the heat loss actually decreases at a constant rate from 31 degrees Celsius all the way down to 0 degrees Celsius. Okay, so this assumption is actually not valid. In real life, the rate of heat loss is actually decreasing. Okay, it's not a constant rate. So, and this is one of the reasons why you'll find that it takes a longer time actually for the object or for the water actually to cool down between, let's say, maybe 10 degree to 0 degrees Celsius as compared to 30 degree to 20 degrees Celsius, even though the difference is 10 degrees Celsius. So the 10 degrees Celsius at the beginning actually is faster than the last 10 minutes. Sorry, the heat loss at the initial 10 minutes as compared to the final 10 minutes. The final 10 minutes actually needs a longer, heat loss is actually lower. Okay, so the heat loss is actually slower at the last 10 minutes. Okay, so just take note of this assumption that we make, or this reality check that we are dealing with. Now for question 5. Question 5, okay, is electrostatic. Okay, now same thing here is explain how the paper become negatively charged. Okay, remember paper we are looking here is insulator. Okay, insulator, the only way I get charged for insulator is actually by friction. So one of the important things you have to mention in your answer is by friction. Okay, and in this case, the question mentioned that is negative charge. Negative charge, it means that it is acquiring electrons from somewhere else. And the somewhere else is actually what we know as your pads. Okay, the nylon friction pad. So which means your nylon friction pad, okay, it actually loses electrons, okay, to the paper itself. And through what process? Through the friction process. So in this question, I will need two things. I will need students to highlight to me that is charging by friction, and more importantly is to tell me how is the electrons being transferred. Okay, it has to tell me the direction from the pads to the paper itself. Now, how does this method allow the glue droplet to spread out and stick to the paper easily? Now, take note the glue droplet here. One of the clue that we mentioned is glue droplet, and the clue lies in the fact that it is aerosol. Okay, now the aerosol spray is positively charged. So between the glue is actually positively charged. So the glue droplet is positively charged. And what does it happen? Yeah, and what does this impact? Okay, it's because the fact that the glue is positively charged. Okay, you'll find that the glue actually attracts to the paper easily. And why does it do so? Is because of unlike charge. Okay, because of unlike charge, the glue actually attracts, okay, to the paper much more easily. And similarly, you'll find that, okay, the other advantage that we have when we have using positive charge glue and negative charge paper is that when your glue droplet, because they are the same charge, you'll find that the glue you will not have multi-layer glue, you will not have glue layer on each other because of the fact that the glue is actually light charge. Okay, and light charge, what you have is that they tend to repel each other. So as a result, you'll find that the glue actually spread out. It will spread out automatically because of the same charges hold by each droplet. They will tend to repel each other, and what it does is actually cause the paper to spread out evenly. So in this question here, there's actually two advantages. First advantage is that the glue being positive charge, it allows the glue to stick to the paper more readily. Okay, so the second advantage we are looking at, because the glue is positive charge now. Okay, because it is positive charge and because the glue are all positive charge, you'll find that the glue itself will not attract each other. They will actually repel each other. And what it does is actually cause the glue to spread out evenly onto the surface itself. Okay, so you would not have a scenario, you will have very little chance to have the scenario whereby layer of glues are stick onto each other. Okay, because in this case, the glue droplet actually repel each other. Right, so this is one of the two advantages that we actually tend to use charge droplets on charged paper. Okay, these two reasons are the two reasons why we use charge. When we spray fertilizer, we always want to spray the fertilizer. We want to charge the fertilizer droplet first before we spray onto the crops, because we charge fertilizer, it allows us to ensure that the fertilizer will be attracted to the plant itself, and the charge fertilizer will also ensure that the fertilizer will not be stacked onto each other, because the charged fertilizer will actually repel each other and spread out evenly. Electric field 5.2. Okay, I will not go through this because it's quite a standard answer whereby students, you need to know the field pattern for positive charge, negative charge, light charge, and opposite charge. For question 6 here, question 6 deal with light, to be exact, refraction. Now, what we have here is based on information. You'll find that the question here, the ray form a angle of 36 degrees with the water surface. So which means that the ray that we shine, okay, onto the surface of the water. Okay, so this area, this is the normal. So based on the question is that this is actually 36 degrees. Okay, now this is the light ray shine onto the onto the surface. Now, based on the question is that you have a reflecting index of 1.3 and calculate the refraction ray in the water. Now, the common thing that we are looking at is refraction. The formula that I always remind students to take note is this formula. Okay, reflecting index is equal to sine, okay, angle in the less dense medium, okay, divided by the sine of the angle in the dense medium. But in this case, we are looking at air. In this case, this will be the less dense medium. And the dense medium we are looking at is actually the water here. So the water will be dense medium. Okay, then the other thing that I always caution students when doing light or refractions or using the formula is that the fact that the angle that you are concerned, it has to be measured from the normal to the light ray itself. Okay, so this is the angle in the less dense medium. Okay, which is 90 minus 36, which gives us 54 degrees here. Okay, so 54 degrees is the one that you're looking at. Then after that, there will be an angle of refraction. Okay, so the light ray will pass through the water and you will see your angle of refraction. He will bend towards the normal. So let's say this way. So this will be the light ray. Okay, so remember angle, and when we're looking at light ray, is always measured from the normal. So this is the normal. So this is the angle that I'm looking for. This is what we call your angle in the dense medium. Okay, so once you have located these angles that you're interested in, all you need to do is substitute the numbers into the formula. just take note, the refracting index 1.3, okay, is given. Okay, so if you look at the working, if I will actually use the formula, and it will be 1.3 equal to sine angle in the less dense medium, which is 54 degree, divided by angle in the dense medium. So this is the formula I'm looking at. Okay, or you can use this formula. Both are the same. Okay, so once you have this, you'll be able to find angle D will actually be 38.5 degree. So this will be 38.5 degrees. Okay, quite easily done. Part B tell us to draw the light ray that the girl will be able to see the earring. Let's say we choose, my eye will actually see the image. Okay, my eye will actually want to see the image. Okay, so the assumption that my eye will make is that the light ray will actually come from the image itself. I will be able to see the object, and light ray actually travel in straight line. Okay, and from my experience, you will know that actually the image of the light ray, okay, will actually he will actually find that the image will actually travel in a straight line, and the object will actually travel in a straight line. So your eye will assume the light ray will travel in a straight line. Okay, so you will travel in a straight line. Okay, and you enter your eye, it will travel in a straight line. So which means that the light ray, this light ray here, it will have to be traveling in a straight line. So the moment you receive this light ray, your brain will automatically extrapolate this light ray all the way back. Okay, all the way back in this section. It will be in a straight line because your brain will assume that light ray travel in straight line. Okay, and sad to say is that it doesn't travel in straight line. Okay, because in this case it passes through 2 medium, but your brain doesn't know that. What happened in the real scenario is that the light ray actually comes from the object itself, and the object actually hits the light ray here. Okay, so this is the object coming in. Okay, light ray from the objects, it hits the surface of the water at these surfaces, and the light ray actually enters. Okay, it actually enters our eyes. Okay, so this is the light ray that we are looking at. So this is the light ray that we are looking at. Okay, so the blue color is the actual light ray that we see from the object, but your brain will actually extrapolate. It will thought that it's coming from a straight line. So he will have this dotted line here. Okay, and how we know where is the image? You will find that the image will always be directly above the object itself. So this area here would be the image of the earring. Okay, so by experience, you will find that the object will actually be slightly above the object, and as a result of the refraction, you will find that your brain doesn't register the refraction. He will thought that light ray come from a straight line, and as a result, he will actually extrapolate the light ray to the back of the incoming ray. So that's where you get the yellow color, the highlighted ray. So your brain, or what you actually see physically in real life, is that the object is actually above. Okay, the image of the object will actually be above the object itself. So what we call a floating object. And so this will be the answer that you are seeing. Okay, I have a slightly computerized picture here. You may want to take a look. Now for part 2 here, for part 3 here, right, the question talk about internal reflection. Now remember, the condition for internal reflection, there are 2 conditions. Okay, for internal reflection is that it must always travel from dense medium to a less dense medium. Okay, your optically less than medium, optically dense medium to optically less dense medium. That's the first condition. Second condition for internal reflection to occur, your angle of incidence must always be bigger than the critical angle. So if only upon fulfilling these 2 conditions, then your internal reflection will occur. But however, in this case, when the light ray shine from the torchlight, okay, it's always traveling from less dense medium to dense medium. Okay, so because of the first condition, because of the direction of travel, it's always on less dense to dense. So which means the first condition will never be fulfilled. Okay, and because of that, you'll find that because the first condition will never be fulfilled, whatever angle you use, okay, you will not achieve total, you will not be able, the ray will not be able to undergo total internal reflection at all. Okay, because the condition is not fulfilled. The first condition is not fulfilled. The direction of travel is wrong. Okay, so in this case, the students, you have to highlight to the marker that the direction of travel, which is less dense to dense, is actually wrong. Okay, it's actually not traveling from dense to less dense. Okay, only when you travel from dense to less dense, then total internal reflection will occur. Okay, so take note of the answer here. Now, part B. Part B here deal with like ray drawing diagram, lens drawing. Yeah, lens drawing here, the thing to caution is the magnification. Okay, is the 1 cm long. Okay, the 1 cm long is actually denoted on the picture here. So if you look at this drawing, is like what we call a scale drawing. But the good news about this drawing is actually quite a standard picture that you see from the 6-ray diagram that you see now on the screen that I put up here. Okay, so I will not dwell too much on this ray drawing diagram. In the upper right corner, I actually inserted the video for lens drawing. But if you have not revised or you like to take a look at how is lens drawing is being done, you can click on the video on the top right side, of the so that you can actually access my ray drawing or lens drawing diagram, so that you can get a quick revision on lens drawing diagram. There's the answer here for you to take a look. Okay, so you might want to check your answer. Okay, the focal length is actually 4 cm. Now, question 7. Question 7 is a circuit question. Now, take a look. Okay, now the heater rated 50 watts. Okay, sorry, 50 volts, 300 watts. Okay, now with a 100-meter long cable, 100-meter long cable. Now, 2 times 100-meter long. So now what's the resistance of the cable? Now, the rating is 300 volts. So I would say this is a simple plug and play with all the standard formula. Now for part B, remember, when we look at resistivity, you look at length, okay, 100 meter and 100 meter. Okay, now the more you look at resistivity, length, and even now you have diameter. So you bring us to a familiar formula known as rho L over A. Okay, you see this formula, rho L over A. Now, this formula is one of the small formulas in circuit that students will have to take note. Now, so this formula, you have to remind yourself that these what are the factors that involve. And in this formula, what are the common tricks that we always like to use? We always like to change, we always like to take note, ask students to calculate the area itself. And in this case, we are looking at the diameter of the area, which is pi r squared, which means the diameter is 0.734. But remember, for area, the specs that we need is I need the radius, not the diameter. So you'll find that with a radius, if your diameter of 0.734, you'll find that the radius is actually 0.367 millimeter. And second booby trap that other than the formula, the second trap that we are looking at is the SI units for each of them. Okay, remember, it has to be in meter for everything. So diameter, okay, don't leave it in mm. You have to change it to millimeter. Actually, you have to convert millimeter to meter first, that in order to calculate the area in meter square. Okay, so once you have these two hurdle being taken out, you'll find that all you need to do is substitute the formula into the calculator, okay, the values into the calculator, and your answer will appear. And so just take note of the small tricks or small booby traps you may occur along the way. Now, calculate the actual power, okay, received by the heater. Now, here you have to take note is that because of the wires, these two wires actually contribute additional resistance, which means the circuit is actually not a 50 volts in parallel with heater. No. Okay, in fact, with the fact that the two cables, the 2 times 100 meter cable has resistance, it means that the 50 watts, okay, is actually connected to actually 3 loads here. Okay, the first one is the resistance of the cable. The third one is also the resistance of the cable. Okay, so 100 meter each on top and below. And in between here, you actually have the heater here. So in fact, that although from the picture here, it seems like there's only heater connected to the circuit, but in actual fact, there's actually 3 resistors connected in series, or 3 load connected in series. Okay, and series, one of the properties that we have is they actually governed by the same current here. So to calculate the potential, to calculate actual power by the heater, okay, to calculate this power over the heater, okay, I can use I square R. Okay, but to get the I square R, I need to know the current here. And to get the current here, I actually need to know the total resistance in the circuit here. Okay, so what I do here is I actually calculate the total resistance. I use the formula V equal to IR. Okay, and I is voltage there, right? Resistance. And now the resistance I'm looking at is the total resistance. So the total resistance consists of the the two cable, okay, which is 8.1 ohms, followed by the resistor in the heater 8.3. So 8.1 plus 8.3 will be the total resistance in the circuit itself. And I have the total potential difference, which is 50 watts. I will be able to calculate the actual current flowing through the cable itself. Okay, and with the current flowing through the cable, because remember they are series, so the current will actually be the same. You'll find that by using I square R, I should be able to get the answer straight away. Now the hard part is here. Now the heater is now replaced by a second heater. Okay, rated 1000 watts. Okay, 240. And connected to a mains of 240, connected to the mains, Now the mains and the heater actually change. Okay, now efficiency, we looking at here. Efficiency, we are looking at useful power. Okay, the most basic formula, useful power divided by the total power input. Okay, now the second heater we are looking at the power input of 1000 watts. Okay, this is the power input of the second heater. Okay, so with 1000 watts input, I will need to know the useful power first. So what we do is we actually need to repeat what we done in part A, B, and C again. So part A, when we look at it, we look at the resistance in the cable, resistance in the heater. So that's same as before. Okay, so now remember what we did, we replaced the heater. Okay, so in this question here, we replace the heater. Okay, the cable is still there. This is the resistance in the cable. The resistance in the cable. So this is the heater now. Okay, the power supply, we also replace it with a 240 power supply. Okay, the current inside here. So the first thing that we do, what we did in part A is we actually we want to identify the resistance in the heater. And from there, we continue what we did in part C. I will actually identify the current flowing through the circuit, because this is a series circuit again. And I will be able, if I have the current in the circuit, I will be able to calculate the power in the heater using the formula I square R. Okay, so once I have the power of the heater now, this power here, this value here, will be the what we call the useful power. Okay, by this heater here. So in this case, you'll find that based on the question here, I will actually identify this is what I did. I calculated the resistance of the heater, the new heater now, and I calculate the current flowing through the circuit. And from there, I actually calculated the useful power of the heater now. So now the useful power heater is actually 751 watts. Now, so what I did additional, okay, is that I move one step ahead to calculate the efficiency. Now, efficiency for second heater, the useful power is, this is the power useful, which is 751 watts. The power input is 1000 now. This is the power inputs. Okay, so I will have an efficiency of 75.1%. The previous heater we are looking at, remember the previous heater based on the rating. The previous heater based on the rating, this is the 300 watts, which means this is the power inputs. The power output for this heater we have calculated is 75 watts. This is the output power, or what we call the useful power. Okay, so with these two numbers, I will be able to calculate the efficiency of the first heater. Okay, which is interestingly efficiency of 25% only. So 25% compared to 75.1, you'll find that the second heater is actually much more efficient. Okay, so this is what we mean by the using the working by means of calculation to prove that which heater is more efficient. And in this case, we will find that the heater in the second heater is actually much more efficient. Okay, as a heater. Okay, it uses more, 75% of the power input is actually used for heating purposes. Now, what happened now is that the question linked it to a earth wire and a fuse, okay, for safety reason. Okay, now the question explicitly tell us how the fuse and earth wire protect the user, earth and fuse. So students, you have to take note, we are not just looking at fuse or earth wire, we are looking at both of them. And okay, so now what happened is we will look at the first pattern. When we look at fuse and earth wire, there's only like one way of looking at it, is whereby you look at earth faults. Okay, so when you have earth fault, few things that you need to take note is that when you have to tell the markers that the earth wire is actually when the current flow through the earth wire. Okay, you'll find that at this moment in time when current flow through the earth wire, the casing is actually live. And why does current flow through a metal casing? Is because the live wire. Okay, I will insert this live wire. The live wire touches the metal casing. Okay, and this is one of the main reasons why Earth is live now. And this statement is actually mentioned by the question itself. So when a live wire touches the metal casing, it does that the current actually flows through the Earth now. Okay, so now the Earth is live. Okay, so but what happened here is that's where your fuse come in. Because what happens is when your live touches the Earth wire, when you have a current flowing through the metal casing, when current flowing through the Earth wire now, you'll find that the current flowing through will be of a high value, and this value usually exceeds the fuse rating. And as a result, the fuse will blow or the fuse will melt. And what happens is that it will actually disconnect the appliances from the high voltage. Okay, isolate or disconnect. I will use isolate or disconnect. And what it does when once I disconnect the earth wire, once I disconnect the appliances from the live voltage, the high current in the metal casing will be cut off straight away. And as a result, I will be able to protect the appliances and indirectly protect the user. Okay, so this is how earth wire and fuse work hand in hand with each other. Okay, so when you have a fault in the earth, okay, the current will be flowing the earth wire. So how do I cut off this current supply? Is where the function of fuse. The fuse will actually melt and you actually cut off the current flowing through the metal casing. Okay, and this is how I look at how I explain the usage of earth wire and fuse together as a team. Okay, to actually protect the appliances and the user also. Now for question 8 here, we are looking at magnetic field lines, okay, rotating, okay, based on the question is rotating anti-clockwise at a constant speed. Now, part A here, okay, explain how the EMF is induced. I would say this is quite a standard questions. Okay, now EMF induced is what we call your Faraday law. Faraday law, when you look at Faraday law, you're looking at the rate of change of magnetic field lines. Okay, and you have to take note is either you tell me the changes, this statement, or you tell me there's a rate of change in magnetic flux. Okay, so either way I accept. Here is a standard answer that we always look at. Okay, so either you tell me rate of change in magnetic flux, or you tell me there's a change in the magnetic flux per unit time, cutting the coil, etc., etc. And after that, the EMF will be induced. Usually, I will tell students, other than stating these two, I also move one step ahead to tell the student to write the magnitude of the EMF. The magnitude of the EMF, okay, EMF induced is actually proportion to the rate of change of magnetic field line. Okay, to the rate of change of magnetic flux. Okay, so usually when we look at Friday, I always remind the students to actually write down these 3 points, okay, to have a standard set of answers for magnetic flux. Okay, so it's easier for students to actually navigate through all the sea of keywords. Now state the smallest angle such that the induced EMF has the maximum value. Maximum EMF. Okay, the orientation should be the coil should be horizontal, or what we call it, the coil is horizontal. And when we have minimum EMF, what's the orientation? It has to be coil, has to be vertical. Okay, so these are the two orientation that we have to take note when we look at the EMF induced. Okay, for the maximum EMF, the coil has to be horizontal, so which means horizontal. So my X has to be what we call 90 degrees. Okay, so the answer here there will be 90 degrees. Okay, whereby I have a maximum EMF. Now we look at the coil connected to CRO. Now, what's the function of slip ring? Okay, slip ring is standard answer for AC. I would say for AC generator, the standard parts, the labeling, what's the function of slip ring, what's the function of carbon brush. For DC motor, what's the function of split ring, what's the function of carbon brush. These are the components that we have to take note of. Therefore, for slip ring, okay, to transfer the current from the external voltage or external current from the slip ring, from the coil generated, can be transferred from the ring to the external brush to the external circuits. Okay, so your split ring is like a pathway, a gateway to connect the internal circuit, which is the coil, to the external circuit, which is the load. Okay, draw the arrow. Okay, now the arrow for ABR. Now, when you are rotating clockwise, so here we are looking at Fleming right-hand rule. So the coil is, the magnetic field line is from north to south. So this is from north to south. So this is your magnetic field line. And the force is actually upwards. Wait, give me another color. So the force is actually, the motion is actually upwards. So this is the force. Okay, so you'll find that if you use a Fleming right-hand rule, this will be an index finger. Okay, then this will be your thumb. And you'll find that your middle finger will be the direction of the current itself. So in this case, the middle finger will actually point in the direction of B to A. Okay, so if you use a Fleming right-hand rule, you will find that the current will actually flow from B to A. Okay, quite easily done. Remember, it's Fleming right-hand rule. Okay, same thing as before. Okay, explain how the induced current oppose the change then. Okay, remember, the induced current will always flow in the way to oppose the change. Your magnetic field is in this direction. Okay, this is the magnetic field. Okay, this is the north. This is the south. Now, how does this induced current work? Remember, it has to oppose the motion because of Lenz's law. And how do we know the direction? Remember, the coil is rotating anti-clockwise. Okay, and how do you know the force? How do you know the force induced? Okay, when looking at finding force induced, we will actually employ your Fleming left-hand rule. So in this case, this will be your index finger. Okay, if you use left-hand rule, this will be the index finger. And your current will be your middle finger. Okay, and if you use a Fleming left-hand rule, you will find that, okay, the force induced will actually be pointing downwards. Okay, this will be the force induced, which is your thumb. Okay, remember, you are using Fleming left-hand rule. Okay, you'll find that this will be going downwards. Okay, we'll be opposing the motion. The motion you're looking at is the rotation, which is anti-clockwise, which in this case is actually anti-clockwise. Okay, which is actually what we call upwards direction. But your force induced due to your induced current is actually downwards. Okay, to opposing it. So in this case, what we are looking at is because we're looking at the induced current will interact with your magnetic field lines. Okay, and the interaction between the induced current and the magnetic field line will actually induce a force. Okay, and this is what we mean by your Fleming left-hand rule. And because of that, okay, you'll find that these two forces will actually oppose each other. Okay, action and reaction. Okay, they will oppose each other to, okay, and this direction is governed by you can use the Fleming left-hand rule, and you'll find that it's actually pointing downwards, okay, to slow it down. So in reality, you'll find that the AC motor, okay, when you turn, okay, the AC motor is actually not easy to turn. It's actually quite hard to turn because there is actually what we need, and this induced force in the coil to actually oppose your motion. So it's actually not, you will not be able to turn it easily, okay, because there will be some resistance as you turn, and this resistance arises from the induced current, okay, that you generated, that you want. Okay, so this is what we mean by your induced force. Your induced current actually indirectly induce a force as you move, okay, due to your Lenz's law. Now, part 4, okay, you'll find that the rotation is given here. Okay, the trace of the AC motor is given here, And determine the frequency of the induced EMF. Okay, this one I would say is quite straightforward in the sense that you'll find that for CRO, this is one cycle. Okay, and CRO, your x-axis, your horizontal axis is your time base, and or what we call your time. Okay, so if your x-axis, if your one cycle is 4 square, you'll find that this one cycle actually dictates or will actually give you the period of the wave itself. Okay, so 4 square, based on the question, okay, 4 cm. So given that the time base is 10 millisecond per cm, you have 4 square, which means that the period will be 40 milliseconds. And frequency will be 1 divided by t, which will give us 25 hertz. Okay, quite easily done. Now draw the trace, okay, as I half the speed. Remember, half the speed. When for rotation, remember there is always 2 changes. When you rotate, when you change the speed, you always reduce the magnitude, amplitude. It always affects the amplitude. It also affects the frequency. Okay. So for rotations, it always affects 2 factors. Okay, as compared to what changing the magnetic field strength, changing the number of turns of coil. Okay, for changing the speed, you actually have 2 effects. One is reducing, or one is it changes the amplitude. The other one is change the frequency, or AKA it changes the period. Okay, so if you reduce half the speed, you'll be half the amplitude, you'll be double the periods. Okay, so for changes wise, take note of this. Okay, so now with this, this will come to the end of section A. Now let's move on to section B. Now section B, question 9. Okay, question 9 is an interesting question. It has a lot of information. So for students, right, who is doing this paper, you have to read the questions carefully, as in this question is important. For example, right, the first information that's important to us is that the boom, the second statement here is that the boom, okay, is pivoted such that it is 2 meters from the pivoting point to the back of the wheel itself. So which means the boom, the beginning of the boom, okay, to the back of the wheel, there's a 2 meter length. Okay, this length is important at the later stage. Okay, so this information at this paragraph is important. Now, as we subsequently move on, you'll find that the boom, actually this part of the boom is extendable. So if I can extend the boom, okay, to the length that I need, okay, it can be 2 meters, it can be 4 meters. The default length is 2 meters. Okay, then after I can extend it to 4 meters, 6 meters, 8 to subsequently to 12 meters. And after I give information about distance from the load to the back of the wheel. Okay, the back of the lorry wheel is here. This is the back of the lorry wheel. So when I extend the boom, okay, let's say example, the load is here. Okay, so that then with the amount of loads given, okay, then the questions in the table 9.1 also give you the distance where the load is from the back wheel of the lorry. So for example, if I given 3,000 kg, if I'm carrying a 3,000 kg load, the distance from the load to the back of the wheel will be 2 meters. So this length is actually 2 meters. Okay, this is what we mean by the information given on the table itself. Okay, so the table eventually students will need to take note of the table and what does the information actually portray in the picture of the boom itself. Now for question A, okay, question A, using table 9.1 states and I explain the relationship of the distance with the distance and the loads carried. Now based on the thing, you'll find that first, one of the obvious information is that the distance, okay, as the loads decreases, okay, as you move on, the load decreases, the length, okay, distance on the length on the loads actually increases. Okay, so one side you have an increasing, when your load is decreasing, okay, you'll find that the distance from the load actually increases. So this is what we mean by inverse proportion. Okay, so which means what is the distance is increasing while the load is decreasing. So they are like in 2 different directions. That's what we mean by inverse proportion. Then after that, one of the interesting things that you need to take note is that the relationship between the 2 of them, distance and loads. Okay, the distance and loads. Okay, for example, if I convert this particular portion here, if I convert this table to Newton, okay, so which means I convert it to Newton, so it will be a mass times G. Okay, mass times gravitational acceleration, right, your gravitational field strength, okay, which is 10. So this will be 330,000 Newton So this will be 15, then 30 at the back. So you find if I convert, okay, all these to Newton, okay, then you have one relationship whereby the distance, the weight, multiplied by the distance. Okay, you'll find that if you multiply these two together, it will give you a unique number known as your turning effect, the moments. Okay, the moments by the loads. Okay, this information will give you the moment of the loads. Okay, of the load itself, which is distance times perpendicular distance times the weight. You'll find that you always end up with a number. The moment by the load is actually a fixed number, okay, which arrives to 60,000 Newton meter. Okay, so this information that we're looking at is the second thing that we can actually observe from the table 9.1. Okay, that's the product of them, the product of the distance, or what we call the turning effect of the load itself, is always 60,000 Newton meter. And so these are the two information that we can elicit from the table given. Okay, now next is we are looking at the weight of the uniform boom. Okay, now we have the weight of the uniform boom is 10,000 Newton. The boom itself, the keyword is uniform. Okay, what's the minimum weight needed for the lorry? Assuming that the CG, okay, of the lorry is 2.5 meter from the back wheel. Now, the easiest one is you look at the diagram given. Okay, the marker is very nice. Okay, when doing the answer, he actually inserted a diagram which actually illustrates very clearly how the whole interpretation from table 9.1 and figure 9.1, how should it be interpreted. Now, for example, if I want the minimum weight, what am I looking at is, I'm looking at what's the load, how can I balance it with the loads that's going to be carried. Okay, so I'm looking at, let's say if I'm looking at the maximum length, this is the maximum boom length extendable. Okay, so when I am at maximum length of 12 meter, based on table 9.1, okay, at 12 meter boom length, okay, the distance, the load I can carry is actually 6,000 Newton. Okay, and the distance from the load from the back wheel is actually 10 meter. So which means this is what is happening here. So this is the weight, this is the load itself. And this is the 10 meter that's given in the question. Okay, so these two information is actually elicit from the table itself. Now, after that, you are given one more information. You are given the weight of the boom. Okay, the weight of the boom is on the uniform boom. So which means at the length of 12 meter, the boom is actually at the CG, okay, or at the middle of the boom, which is 6 meter on the right and 6 meter on the left. Okay, so this is where the boom is. Okay, this is 6 meter. Okay, so this is the loads of the boom itself, the weights of the boom. So how do I know it is 4 meter from the back wheel? How do I know it is 4 meter from the back wheel? One information that I remind students to take note is actually the beginning picture. At the beginning of the picture, you'll find that the boom, the starting point of the boom is actually 2 meter from the back wheel. So which means that this 2 meter is actually here. And I know that the right side of the boom is actually 6 meter. And if I know the front part is 2 meter, I will know that the back part here will be 4 meter. So that's why I know that the weight of the boom is actually 4 meter from the back wheel. Okay, given the information I have from figure 9.1. Okay, so this information is actually important. Okay, because later on the distance, okay, will be needed to calculate the moment of the boom. Okay, by the weight of the boom itself. Now, the other one that the students might ask is, how do I know the weight of the lorry? Is it on the left side of the back wheel or on the right side of the back wheel? Okay, now there's a slight deduction that we are looking at. You'll find that on the right side of the wheel, on the back wheel, okay, you'll find that weight of the boom will give rise to a clockwise moment. The load itself will also give rise to a clockwise moment. So for the lorry to be balanced, there need to be at least one anti-clockwise moment to balance out. So where does the anti-clockwise moment come from? The anti-clockwise moment will come from actually the weight of the lorry. So that's why I know the weight of the lorry is actually in front. Okay, it will be in front. Okay, so this will be the weight of the lorry, which will give rise to the front part of the at the left side of the wheel itself. And how far is it from the back wheel? Based on information given, okay, I will know that the question mentioned that the CG of the lorry is actually 2.5 meter away from the back wheel. Okay, so now I know the 2.5 meter is actually on the front side of the back wheel. So this will be 2.5 meter, where we should give rise to an anti-clockwise moment. So this is the weight of the lorry itself. So now I have a standard moment equation whereby I have actually the clockwise moment. Okay, this is the moment of the load itself, and this will be the moment of the boom itself. Okay, so these two will be a clockwise moment. Then after that, I will have the anti-clockwise moment, which is controlled by the weight of the lorry itself. Now, for the moment of the loads, okay, the force is 6,000 Newton, and based on the question is for the force to the back end of the to the back wheel, and based on information it is actually 10 meter. So which means you will know that this is actually your, so if your moment of the loads, it will be 6,000 okay Newton times 10 meter, which is the perpendicular distance given in table 9.1. As for the weight itself, the force that we are looking at is the weight of the boom, which is 10,000 Newton, which is here. And based on the analysis I mentioned to you, the weight is actually 4 meter from the back wheel, which makes the perpendicular distance 4 meter. So this portion here will be the weight, the moments of the boom itself. Okay, you will balance out with the moments by the lorry. Okay, so this is the moment of the lorry. It should be M, moment of the lorry. Okay, so the weight would be the force, and the distance will be 2.5. So once you have the equation here, once you have the equations, okay, you go ahead and actually simplify, and you will find that the weight of the lorry given will actually be 40,000 Newton. Okay, so that's why I know the answer here will be 40,000 Newton. Now, B1 actually is although B1 is the initial part, you'll find that although it's the initial part of the question, but it's actually not easy. But to get the equations, the clockwise and the anti-clockwise, this concept is, I will say, straightforward. But just like because this information, the data, the variables in the equation actually they are derived from table 9.1 and figure 9.1. So this is where it makes it tricky. Now for part 2 here. Now, based on the question is why at 4 meter boom length, how come the maximum loads is actually the same as what you calculated at the initial part at table 9.1. Okay, so now what actually happened is that when you look at the lorry itself, okay, so this is the front wheel, okay, and this is your back wheel. Okay, so this is the front. Now your boom, okay, based on the picture of boom, is somewhere in the middle here. Okay, so this is where the start of my boom. Okay, now based on the question is that the starting of the point of the boom is actually 2 meter here. Okay, so this is the length of my boom. Okay, 4 meter. Okay, and I know that the boom starting point is here, and it's actually a 2 meter length in front of the back wheel. So which means that it will make us that the portion here, this length we are looking at for the back of the boom, is exactly 2 meter. Okay, so we know, so at 4 meter length boom, you will find that actually only 2 meter of the boom is actually beyond the back wheels. What does this implicate? Okay, to the question, it tells us that the boom, which is a uniform beam, the CG will have to be at the 2 meter mark. So this is the weight of the boom at the 2 meter mark. Because I have a 4 meter boom, so the weight of the boom will have to be exactly at the middle, which is 2 meter mark. Now what happened is at this particular position, at this particular length of boom, 4 meter, the weight, since the weight is actually at the pivots of since it's actually directly above the pivoting point, which is the back wheel here, you'll find that there isn't any perpendicular distance. So which means the weight of the boom itself at 4 meter length boom, right, the 4 meter length, you'll find that the weight of the boom is actually directly above the pivoting point. And because of that, it will mean that the perpendicular distance, okay, of the weight, okay, between the pivot and the weight of the boom is actually 0. And this will mean that the moments derived from the weight of the boom is actually negligible, or it's actually it doesn't play a part, it doesn't create any moments. Okay, because the fact that there isn't any perpendicular distance between the weights and the pivoting point. Okay, so these are two important factors that we have to take note. Okay, because of the particular location of the weight itself, it leads to the fact that there isn't any perpendicular distance, and because there isn't any perpendicular distance, you will find that the moments actually is zero. Okay, so the weight of the boom doesn't contribute to the additional loads or additional turning effect. And thus, okay, the weight of the lorry will be able to balance out the load that is being carried out, okay, by the lorry itself. Okay, this is what is depicted in the particular scenario here. Okay, so as such, okay, because of the lack of moments due to the weight of the boom, okay, the loads, okay, is actually exactly the same as what we calculate. What is shown is actually 9.1. Okay, no additional. The load won't be like the load carried won't be lesser as represented in 9.1, even in the actual case. Okay, so just take note of this particular section here. So part A and B is actually quite, I would say it's actually quite tough, because students, you need to actually derive the information from the table and after interpret it using the concept given to actually derive the answers that is required, which can actually be quite tough. Okay, then after that, for part C, there will be additional support. Usually for crane, if you are sharp enough, you'll find that even in day-to-day cases in real life, you'll find that before the crane operator, before they start operating the crane, you'll find that they will always extend the base. This extension link, they will extend out. Okay, this is what we call support. Okay, they will extend out of the lorry itself. And one of the primary reasons for them to increase this, or to have this additional support, is actually to increase the base area. Because remember, the two common factors that we have is we need to lower the CG. Okay, the common factor for increased stability is lower CG, and actually the other one is what we call known as a broad base. So by increasing the additional support, by lengthening the additional support, okay, you'll find that I'm actually increasing the base area. Again, thus where you'll find that the CG will be, okay, will be rotate more. Okay, and such that the CG will also be in the base area before toppling. Okay, this is one of the most important factors that we have when we look at increasing the base area. Now for question D is totally another different story here. Now what happened here is you have, okay, the freely suspended. Okay, now freely suspended, you have to be careful. Freely suspended, one of the hint, this actually gives us the hint that the weight, in this sense, that the concrete beam is actually in equilibrium. Okay, it's actually stable in this sense. So stable, it will mean that there isn't any rocking, there isn't any turning effect, and when it doesn't have any turning effect, it will mean that the CG, the moments, will actually be zero. So when the moment is zero, it will mean that the pivot or the weight of the concrete beam will actually be directly below the pivoting point. So this is the pivoting point, so it will be directly below, okay, the pivoting point. So this will be the what we know as the CG of the concrete beam. Because the CG is actually directly below the pivot, and thus it makes the perpendicular distance, okay, between the forces and the pivot to be 0 meter. No perpendicular distance, no turning effect. Now the part two is dealing with density, or what we call some mathematical calculations regarding density. Now the important factor here that we're looking at is that the concrete beam consists of 10% steel and 90% concrete based on volume. Okay, so based on volume, so when we're looking at density, density is actually mass over volume. What is interesting, or what is difficult among this, that this beam is actually an alloy. So when we're looking at density of alloy, I actually need the mass of the alloy and the volume of the alloy. Okay, so in this case, the alloy is consisting of the steel and concrete. So I will need to know the mass of the steel, and I also need to know the mass of the concrete itself. Okay, together, I also need to know the volume of the steel, okay, the volume of the steel needed, okay, and the concrete itself. So what we call known as the total volume here. Okay, so you don't write SC, you can write the total volume here. Okay, the total volume. Okay, so how do we go about doing it? Okay, so now we have to find, first thing we have to find the mass of the concrete and steel. Now, based on How do I find the concrete? How do I find the mass of the steel? Mass of the steel. This is mass of the steel. So to find mass of the steel is actually what we know as density of steel multiplied by the volume of steel. Okay, so the density of steel, which is here. This is density of steel. Volume of steel based on the question, I can actually represent it in terms of total volume. So it will actually be 10%, 0.1 of the total volume. So this V actually refers to the total volume. Similarly, for mass of concrete is actually density of concrete multiplied by the volume of concrete. So same thing, the volume of concrete, density of concrete is given in the question. Okay, 2400. Okay, then volume of concrete, I can actually represent it in terms of total volume, which is actually 0.9% or 90% of the total volume. So from here, you do your algebra or you do your cancellations of common factor, you'll find that the V and V can cancel. Okay, and after that, if you simplify you use your calculator, you simplify your answer, you'll find it to be 2940 kg per meter cube. Okay, I wouldn't say it's difficult. It sounds like a bit of like math. So I wouldn't say this is difficult. It's just that it might be a bit tedious. Now for question 10. Now question 10 deal with solenoid compass. Okay, so now let's take a look at this. Now, for question 10 here, you have your solenoid and your compass here. And based on information, okay, you'll find that the information given is that you have a north pole being induced on the right end of the solenoid. So which means based on the picture, you'll find that you have a solenoid based on the induced on the right side. And automatically, you will know that the other side will be a south pole here. Okay, now draw the arrow on the right side, draw the arrow on the left end, okay, to indicate the direction of current through a solenoid. Yeah? Now here you will need to use your Maxwell rule, Maxwell right-hand grip rule. Okay, for you to use Maxwell right-hand grip rule, remember your right side, your thumb should be pointing to the right side. Okay, your thumb should actually point to the north side. So if you curl it, you'll find that if you curl your fingers, you'll find that using Maxwell right-hand grip rule, you'll find that current is actually going downwards. So which means this area, the current will be going downwards in this arrow here. So you'll be in the front, you'll be coming down. Then so you'll be going into the paper itself. So you'll find that the coil will actually be, the current will actually be going down on the right side, and you'll actually be going up on the left-hand side. So it will mean that it will be equivalent to having a battery that is on the positive terminal is on the left side, okay, which is what I mentioned here. Okay, so this is what means the final outcome of this will be the answer for the final outcome, okay, for the solenoid. Okay, using your Maxwell right-hand grip rule. Remember, Maxwell right-hand grip rule, okay, it's a solenoid, means the thumb actually points to the north, actually point to the right side. Then after that, compass is placed on the left hand. So if the compass is placed on the left hand, you will know that compass, remember the compass, the arrowhead symbolize the north pole. Okay, so if this is the south pole, it means that if this is the south pole, okay, it means the arrow will actually point towards the right side. So the compass needle will also point to the right side, because by the compass needle, the arrowhead represents the north pole, and you have what we call a unlike pole here. South and north, they will attract. Okay, so the arrow will actually point to the right side. Okay, so A and B is done. So what happened in part C here is actually I modified this system. Okay, so I have now a DC motor, and a permanent magnet is actually replaced with a solenoid. Okay, so now remember, if the same current flows, okay, you will find that the south pole is here, the north pole is here. Okay, so this is current, this is current. Okay, so now this is the south pole. Remember, magnetic field always flow from north to south. So if my south pole is on the right, I'm actually saying that in my magnetic field line, okay, it will be this way. Okay, so this will be the field line, magnetic field line direction. Okay, now, so let's take a look. Okay. Oh yeah, one important information. This is the positive terminal of the battery. So which means my current is actually going inside. Current is going out at CD. Now from here, let's take a look at the question. Now the arrow on wire AB on the direction of force, force induced, direction of force induced. Okay, direction of force induced, it means I will need to apply Fleming left-hand rule. Okay, Fleming left-hand rule. So now on the wire AB. Now on the wire AB, you remember the current is pointing into the paper. Magnetic field line is from left to right. Okay, left to right. So we use your Fleming, your Fleming left-hand rule. So you'll find that your field line is your index finger is pointing to the right side. Your current, your middle finger is pointing inwards. So it will mean that the force applied, the force which is your thumb, will actually be pointing downwards for wire AB. Okay, so which means my force induced, okay, will actually be downwards. Okay, my force induced will actually be pointing downwards. Okay, so this is what we mean by using a Fleming left-hand rule. Okay, so remember the symbolized for the magnetic field line is actually pointing to the right side because you have a south pole on the right side, and magnetic field line always flow from north to south. That's where your index finger should be pointing to the right side. Current actually inwards AB based on the battery. You let go of thumb, you'll find that AB will actually be pointing upwards, and automatically you will know that your DC wire CD will actually be pointing upwards. So between the coil will actually rotate. Okay, what we know as your anti-clockwise. Okay, so this is what we have for this particular DC motor. Now, so now what happened is explain how the force is induced on the wire AB. There are a few ways to answer this question. Okay, first way you can look at it is you can look at the interaction of the field lines. You can explain Fleming left-hand rule using the interaction of field lines, whereby which the top portion of the wires is a stronger magnetic field lines than the bottom side of the wire, and as a result, you have this force exerting from a stronger in the direction of a strong magnetic field lines to the weak magnetic field line, which is what the answer here is actually derived. The other way of looking at force induced is actually to use Fleming left-hand rule. Okay, so by identifying what is required in the Fleming left-hand rule, which is the current and the magnetic field line, and looking at the interaction between the two of them, the interaction between the field lines and the current at a certain rotation, what we call perpendicular rotation, and this will arise to the force being induced in a specific direction. Then after that, you have to go ahead to tell me what specific direction am I looking at for this force induced. So by looking at these 3 pointers, you are actually able to clearly explain how the force is induced using Fleming left-hand rule. Okay, so if you look at Fleming left-hand rule, I repeat again, there is actually 2 ways of looking at it. Okay, so whichever way you actually are comfortable with, okay, and you are confident with, okay, you feel free to use any one of them. Okay. Now, for part 3 here, we are looking at explaining the feature that allows the DC motor to turn, okay, in the same direction, or what we call 360 degrees without any hiccups. Okay, and this is also what we know as the primary function of your split ring commutator. Okay, or aka this question is asking you to actually explain or define the function of the split ring commutator. So this one will be, I would say, is a standard questions that we always ask students regarding DC motor. So students, you should be well versed at the parts of the DC motor. For example, the purpose of the split ring commutator, the purpose of a carbon brush, and why do you use carbon brush. Now, part D here, we deal with another component of your DC motor, which is your iron core. So students, you have, other than split ring commutator and carbon brush, you have the third component here, which is listed here, which is your soft iron core. What's the purpose of it using in the DC motor? Okay, which is actually one of the primary reasons, okay, which is to actually to concentrate the field lines, okay, to maximize the interactions or to maximize the rate of change of magnetic field lines that is actually experienced, okay, and thus, okay, creating a larger induced force, okay, and thus a larger rotating moment. Okay, so that's the purpose of us using soft iron core. State how to draw the magnetic field lines on the south pole of the pole and south pole of the magnet and the iron core. Now, here one thing to note for iron core, it will be induced. There will be some induced pole happening. For example, since I have a north pole on the left side, I will have induced south pole on the left side of the iron core, and conveniently, I also have a north induced, okay, on the right side of the iron core, which tally with the south pole of the magnet. So here I will have a typical north pole, south pole magnetic field line. It will be north Okay, so these will be the field lines that's experienced by the, okay, between the iron core and the south pole itself. Okay, so this will be the answer that's given. Now, explain how the iron core is induced in the magnet. Okay, so basically, I would say this question is actually similar to how magnetism is actually induced on magnetic material. So how iron core is induced in the magnet. Okay, so important thing is to talk about two things. Okay, it's about alignment of magnetic domains. And once the alignment of magnetic domain is mentioned, okay, alignment of magnetic domains, okay, you will find that this alignment will actually lead to field lines concentrating through the iron core. Okay, so by aligning the magnetic domains is actually the first and primary purpose of getting the material to be to possess magnetic properties. Okay, because the alignment of magnetic domains give rise to the concentration of magnetic field lines, and which give rise to the magnetism properties. Now for 11E, either is a energy question. So you have a roller coaster, electrical motor, and the track here. Okay, so now part A, look at how we can use the principle of conservation of energy when we move from part A to point A to point B. Now, before we can explain correctly, we need to understand what's the behavior at point A and point B. And one of the important information is actually this particular segment here. Okay, which means at point A to point B, there is actually constant kinetic energy, constant speed. So which means that for the speed at A and the speed of B, they are actually the same. So which means from point A to point B, there isn't any changes in the kinetic energy. Okay, so by just that when I'm moving up from point A to point B, okay, there is definitely electric motor being activated. So there is definitely what we know as your work done. Okay, so there will be electrical energy converted to the used by the motor to actually to do work to pull or to move the trolley up the roller coaster up the segment here. And indirectly, and second one that we're looking at is that actually there is a height increment. So there is definitely an increment in the gravitational potential energy. So whatever energy they were looking at, okay, is definitely from the motor, and after that converted to gravitational potential energy. And of course, is that the end of the? Is it the end? Is the only energy gravitational potential energy? The answer is no. Okay, why? Because the question is looking at the efficiency of the motor itself. The efficiency of the motor is 80%. So which means for every 100 joules are input from the motor, only 80% is actually used for useful energy. And in this case, this GPE or this EP is actually what we call your useful energy. So where does the 20% go? The 20% will actually give rise or will actually be accounted for in terms of your heat loss to the environment. This is the conversion that we are looking at from A and B, whereby the electrical energy from the motor, okay, is actually converted to GPE and also to the heat loss to the surrounding. Okay, so the conversion here is not just one form to another form. It's one form, the electrical energy converted to multiple forms. And one of the main forms that we're looking at is actually 80% here is actually your GPE or your potential energy, gravitational potential energy. And the other 20% we are looking at is actually your heat loss and your sound, your losses to the surrounding. Okay, so this is what we mean by the conservation of energy. Now, so power of the electrical motor. So once we understand that the useful power refer to MGH. So you'll be able to look at it in make use of the 80% efficiency to actually calculate the power by the motor. So remember, 80% okay refer to the potential energy. 100% actually refer to the energy by the motor itself. Okay, the total energy. Okay, so this is what we call your total energy. Okay, so that's why for the first part we are looking at, we are actually identifying the potential energy. So I'm actually calculating the potential energy, and this potential energy is actually 80% of what I have. Okay, so which means this 100 joules of potential energy, this 100,000 joules is actually 80%. And from there, I should be able to work out the other remaining 20%, or should be able to work out the 100%, okay, from my 80%, which give rise to the, okay, we give rise to the total power of the electrical motor here. Now, one thing to caution here is I would say the 80% is potential energy. Then after I calculate the energy at 100%. This step I would say is quite standard for most students. You shouldn't have any difficulty. One of the common booby traps, or one of the mistakes that students might make, is actually the time. Okay, 2 minutes. Okay, now for students who are sharp, you'll find that the numbers I'm using here, or the concept I'm using here, is in terms of energy. Okay, but the question is asking for power. So for energy and power, they are related by the fact that power is actually energy divided by time. Okay, so while I'm looking at the energy, I can actually convert it to power by factoring the time also. So when you factor in the time, which is divided by time, you must remember it takes 2 minutes for the roller coaster to move from A to B. Okay, 2 minutes. Okay, but if you look at the formula, your end time here, it has to be in seconds. Okay, so this booby trap, students, you have to be very, very careful. Okay, so which means the time that you use is not 2 minutes. The time that you should be using should be 120 seconds. Okay, you have to convert your minutes to actually seconds. Okay, 2 minutes has to be converted to seconds. So when you divide it by time, remember, don't just divide by 2. You have to divide it by 120 seconds. Okay, so this is something that we have to take notes, okay, very carefully, because most of the formulas that we have in this O-level syllabus is usually primarily, I would say 80% of it is actually SI units. Okay, so you have to be careful of it. Now, the electrical motor is replaced by one with a larger power. Okay, larger power. Okay, now the fact that larger power, but they have one more condition, is that the speed of the the AB remains the same, which means that the condition is still the same, which means that my majority of my energy will still be given to potential energy. Okay, so although I have a bigger power, but the energy I'm using is actually still the same. But this doesn't mean that it doesn't have any impact. It doesn't mean that it doesn't have any impact. Okay, one of the obvious impact that we're looking at, if you have a bigger impact, bigger input, even though I have the same output, but the time taken to achieve this is actually much smaller, because now I have a powerful motor. I can pull the roller coaster up the A to B at a faster time. Okay, so I can actually pull it up at a faster time here. Okay, so even though the potential energy, it remains the same, the energy needed remains the same, but the time factor actually reduced. Okay, so which means the time taken is actually shorter. Okay, and as such, you will find that although the energy remains the same, okay, but the time taken actually to go up actually greatly reduced already. Okay, so one of the effects that we look at is, although the speeds remain the same for A and B, but the timing actually reduced, which indirectly also gives us one additional information. For me to go up A to B at a shorter time, at a faster time. So which means at this junction here with the bigger motor here, and coupled with the condition, the speed at A and B has to be the same, which means that my speed at A has to be the same as the speed at B. Okay, plus the fact I have a bigger input, and the fact that I have a shorter time frame. This will tell us one thing, that the speed at A and B that we are looking at this junction here, at this part C, with this bigger motor, A and B, as compared to the previous question here, this particular question here, or this initial question here, the speed is not the same value. Okay, so for part A and part B, right, you will find that with the old motor, yes, I still have the condition speed at A and speed at B remains the same. The roller coaster doesn't increase the speed. Part C with the new motor now, okay, the speed at A and speed at B doesn't change. But this information, it does not mean that both scenarios, the speed is the same number. It's not. Okay, both scenarios, remember, the condition that's given in the question is that the speed at A and B is the same. But it doesn't mean that first scenario and second scenario, the first scenario refers to the old motor, the second scenario refers to the new motor. It doesn't mean these two scenarios, the speed is the same number. Right? So students, you have to be alert here. Okay, when we say the speed A and B is moving at a constant speed, it doesn't mean the number is the same for both cases. It just means that for both cases, the speed at A and B is of the same value. But it's just that the speed at the second scenario is actually a bigger number. Okay, so which means for the speed at A at the second scenario is actually equal to the speed at B at the second scenario. But the speed at A at the first scenario and the speed at B at the first scenario is also the same. Okay, but these two numbers, they are not the same number. Okay, so students, you have to be very careful here. Okay, so this is actually one of the important facts. Well, once you are able to reconcile with this fact, this information, make sense of this information, you'll find that the answer at part C will actually make sense. Okay, for me to go up at a faster rate, a faster timing, given that the same energy is the same, okay, the object, the speed actually has to be a higher number, even though they are the same number. Okay, or what we call the acceleration of the object is actually larger. Okay, now at part D here, we are looking at point C to point F. Okay, point C to point F, and the question is asking for point E, the point in between the two segments here. Okay, the answer that the conversion energy here, you can look at it in terms of loss in potential energy to gain in kinetic energy. For personally, I'm not comfortable with using loss of gravitational potential energy to gain in kinetic energy, because sometimes I find it's quite difficult for students to actually see the differences. So what I like to do is I always like to go back to basic to look at the energy at each stages, how they are converted. So from, let's say we are looking at point E. So at point E here, the energy I'm looking at is actually gravitational potential at E, which is the 18 meter, and the kinetic energy at E. Okay, then I'm actually coming from point C. Point C, we are looking at the potential energy at C and the kinetic energy at C. Okay, so if you look at conservation of energy, you will find that it's actually converted from one form to the other form. So initial energy is actually converted to the final energy at the point E. So you can look at it in terms of total and initial energy. So for example, I can look at it in this way. So I can have the energy at C to be converted to energy at E. Okay, so they are equal, okay, because they are converted. So same like what I mentioned before, at E, you have potential at E plus kinetic at E. For C, you have your potential energy at C plus your kinetic energy at E. Okay. Now, based on the question, kinetic energy, the speed at C is actually 0.2 meter per second. So you have this number already. So this is what we call your VC. This is what we call your VC. Okay. So now if you submit all the values, you will actually have a nice equation. Let's take a look. Okay. So now MGH at C, H is actually 20 meter. Okay, this is what is given to you. At E, sorry, not E, this should be C, my mistake. Okay, so for half mv squared, okay, so kinetic energy at C will be half mvc squared. Okay, VC squared, remember, is here. This is your VC. Then for EP, okay, at E, okay, is mg 18 meter. Plus your kinetic energy will be half m velocity at E, which you are supposed to find, and square. Okay, so now you have all the numbers here, so you can look at it mathematically. So the most obvious one is the mass. Actually, I can actually cancel out the mass, okay, because they're a common factor. Okay, remember, VC is given. This is your 0.2 meter per second. This is your VC. So you can actually submit the number 0.2 here. Okay, so all the numbers are given. If you rearrange your number, you should be able to arrive at finding your VE, which will actually be the same answer as 6.32. Now, in this case, okay, I give you alternative method looking at the total energy at the initial stage versus the energy at the final stage. Okay, Yeah, if you're not comfortable with total energy, you can look at it like what the marker mentioned. You can look at it in terms of the energy gain, kinetic energy gain, to the energy loss. Okay, energy loss equal energy gain. Okay, it's a classic. Both concepts are the same. Both concepts are looking at energy being converted. It's just that one look at it in terms of loss and gain, the other one look at the conversion, the total. The totality of the energy. Both methods are the same, are using the same concept, just different representation. So whichever you are comfortable and confident, okay, feel free to go ahead and use it. Now, in reality, the speed of the roller coaster is smaller. Okay, definitely. Why is it smaller? Okay, this one is a classic example. Why is it always smaller? Why? Because in this question there, we didn't factor in any rigidity force along the track or even in the track itself. Okay, so along the track, even in point C, point E, all this, there will be friction, and we have not even factored in air resistance yet. So there will be different losses to air resistive force. Okay, it can be the friction due along the track, or it can be air resistance when it's along the journey. So, but either way, is that this will siphon out a portion of the energy. So when a portion of energy is given to these losses, to this resistive force, the energy that is left for kinetic energy will be much smaller portion, and thus, okay, the kinetic energy gain or the speed of the object gain will actually be smaller, okay, than expected. Now for point F, okay, point F is they mentioned there's the average resistive force, so there will be a resistance force here. Okay, so the kinetic energy that you have, okay, is actually given, okay, to overcome the friction and eventually come to a stop. So what we are looking here is that the kinetic, you can look at it in terms of loss and gain, okay, or we can actually look at it in terms of the total energy and the final energy, the total energy and initial energy. So initial energy we are looking at is the initial energy we have is the kinetic energy, okay, at F, and eventually, okay, it will be converted to where? It will be converted at the track, okay, at the end of the track, FG, okay, so you have the work done, okay, by friction at G, okay, and in the question it says that there is some form of elevation, okay, so which means it has to be raised, the track has to be raised so that I can actually let the roller coaster stops nicely at the end of the track. So which means that because of elevated, there will be some vertical height, so there is definitely potential energy at G, okay. So this is what we call your total energy initial. This will be your total energy final. Okay, so you can either look at it in terms of gain and loss, or you can look at it in terms of the total energy. Okay, I always prefer the initial and total energy. Okay, because it's like much easier for students to see at any questions. Okay, so same thing, half mv squared given. Okay, now the speed given is 15 meters, so this half mv squared, which is 15 meters squared. Work done is 10 meter track. Okay, force given is 4,000. So the force will be 4,000. Track distance will be 10 meter. Okay, plus mgh. Okay, gh is what you need to find. Okay, so since all the numbers are given, you should be able to calculate. You should be able to work out the answer. So since all the numbers here are given, you should be able to work out the height to be 3.3 meter. Okay, so same thing as before. Okay, you can look at it in terms of loss and gain, or you can look at it in terms of total energy at the initial. You can look at it in total energy at the initial and total energy at the final stage. So both are using the same concept, just different representation. Now for 11 or. Okay, 11 or is an interesting question. It's rare to see I would say ripples represented in terms of this in this manner, this bright and dark band. It's been some time since I've seen this stuff. This question is actually quite interesting. Now, one thing to take note, okay, you will know that this is actually your crest. Okay, so this will actually be your trout. Okay, so just take note of it. Okay, so remember between crest to crest, it will be actually your 1 lambda. Okay, so one thing to take note, between your crest to crest, or between your trout to trout. Okay, this will be your lambda. Okay, just a small thing to take notes. Okay, so this, yeah, so they means the same. It's just crest and trough. Okay, so now, different region. Okay, and one obvious thing that you take note is that the wavelength of each of them is actually different. So, for example, the wavelength here, okay, and the wavelength here. Sorry, this should be B. Okay, so the wavelength at A and B, they are slightly different. Okay, one is longer, one is shorter. Now, explain why the water wave are transverse wave. Oh, this is easy. Okay, basically, I'm asking for the definition of transverse wave. Okay, so nothing fanciful here. Now, I need to mark out the lambda, which I actually have done it here. So this is actually the answer. Okay, if not, this should be the answer. Now, explain which region is actually deeper. Now, what I want to take note is that the question here. Now, in this question here, we are looking at the same wave. Okay, so in this case, you will find that wave is actually governed by this formula. Okay, so they are actually traveling in the same medium. So which means that the frequency is actually constant. Okay, so frequency is actually constant. Okay, so if frequency is constant, what will happen to the speed and the lambda? Okay, to be exact, okay, both of them are actually related. Okay, so which means that upon entering regions of different depth, you'll find that the speed of the wave actually will increase, will changes. Sorry, not increase, it will change. Okay, and how do I identify the change? It's actually by identifying the change in the lambda, in the wavelength. For example, you'll find that in A and B, okay, you'll find that A and B, the wavelength of A, your wavelength of A and wavelength of B. You'll find that wavelength of A and B, one obvious thing you look at, the wavelength of A is actually much bigger than the wavelength at B. So this will tell us that while transiting from A to B, while the wave moves from A to B, okay, the wavelength actually decreases. Okay, so that's what the question is trying to tell us, or what the picture is trying to tell us. While the wave is going from A to B, the wavelength is actually decreasing. So which means the wavelength is actually decreasing. And when the wavelength decreases with frequency constant, with having the same wave, okay, it will imply that the speed of the wave actually decreases. Okay, so which means that the speed of the wave actually decreases upon entering B. So which means I will be able to derive, okay, I will be able to derive that speed at A and speed at B. Okay, speed at A actually is faster in speed in A is actually faster than the speed in B itself. Okay, so this will tell us that, okay, with the difference in speed, this will allow us to draw one more conclusion. It will mean that the wave is actually traveling faster in A, and this will tell us that actually A is actually a region of deeper depth. Okay, because only when the wave are at deeper depth, they are able to move at a faster pace. Okay, the wave are able to spread out and the speed are able to increase. Okay, so which means that from A to B, the speed actually decreases when you travel from A to B. It will mean that A is actually deeper than B, which means the wave is actually entering a shallow region. So which means my A will actually be deep, my B will actually be shallow. Okay, but remember, when you are having a deeper depth, okay, the wave are able to spread out fast, more, and because of that, they are able to travel at a larger distance. Okay, so the speed will actually be higher. So in this case here, which region is actually deeper? It will mean that A is actually deeper. And how do you explain it? Like what I mentioned, you have to mention about the wavelength of A being bigger than B. Okay, then after you have to mention that the frequency of the wave remain constant for all medium. And from there, you should be able to deduce that the speed of A is actually bigger than the speed of B. And with the deduction that the speed is actually larger at A, you will be able to deduce that the depth of A is actually larger than the depth in B. Okay, so this is how I use wavelength for the wave formulas by looking at the wavelength, by looking at the frequency, and by looking at the speed. And from the combination of these three factors, I will be able to deduce the depth of the medium itself. Okay, so this train of reasoning, okay, students, you have to take note of what how does this work? Okay, using the wavelength to deduce the depth of the medium itself.
Now for part C here, right, it's a one interesting question. The question mentioned the speed of the wave is 20 meters per second. Then he mentioned about the wavelength is 10 cm, which is your lambda is 10 cm. So with these two information, right, it will enable us to calculate the frequency of the wave, which is 2 Hertz itself, or what we call the period is actually 0.5 seconds. So this is one of the information that is like so-called hidden in the question. Then further on, there's one more information, what we know as the center of dark band. Now, center of dark band in this question is one of the crucial things, because center of dark band actually tell us where is the ping pong ball in the actual location. Now, students, you have to be careful that center of dark band, okay, dark band usually implies that, okay, it is actually at the crest of the wave. Okay, if you have dark band, you have another the opposite, whereby you have the bright band. Okay, what we mean as the bright spot. Okay, so you have the bright spot, it will correspond to the trough of the wave. Okay, the corresponding location is important because when we talk about dark band means at the crest. Let me look at the waveform. So let's say this is the waveform itself. Okay, so this is the waveform, the water wave itself. Okay, now take note is that at the crest, okay, when your light ray is coming from above, okay, when your light ray is coming from above, what the light ray actually encounter is this, okay, when the light ray encounter the crest, okay, before hitting, if let's say we take a look at the glass, maybe the floor, the bed is at the bottom here, so this is the bed, whereby you see all the bright region, not in dark region. You find that because the water wave has to, the sun ray has to travel through the water wave. Okay, for those who is at the crest, okay, he has to travel through a larger distance in the water. Okay, if the light ray is incident upon the crest. So upon the crest, okay, you'll find that it has actually go through a large portion of the water wave. And because of the large portion of water wave, more light ray is absorbed. Okay, more light ray is absorbed, or more energy is absorbed. Okay, and when more energy is absorbed, you'll find that the outcome will be a dark band. Okay, so within most of the light energy, the solar energy is actually absorbed by the sun, by the water wave. Okay, by the water wave, and as a result, the amount of energy that reaches the floor is actually minimum. And because of that, you will actually encounter this dark region here. The opposite will be true. Okay, for those who for the light ray who encounter the trough first, the light ray that encounter the trough, you find that the amount of water he has to go through is actually the minimum. So which means upon hitting the water wave at the trough, okay, you'll find that the amount of water, the depth of water he has to go through, right, is actually very little. So as a result, you will find that least energy is absorbed by the water wave. Okay, and as a result of the least energy absorption, the light ray actually retains most of the energy. And what does this mean? It means that upon hitting the base of the floor, the paper or the panel, you'll find that it will form what we know as a bright band. Okay, so student, you have to take note is that when we talk about dark band and bright band correspond to the crest, bright band correspond to the trough of the wave itself. So when this question he mentioned that it is the dark band, it will means that the ping pong ball is actually at the tip, at the top of the wave itself, which is what we call the crest of the wave. Okay, so when we talk about the location, the ping pong ball now is actually at the top of the wave itself. So which means at this particular location, okay, at this particular location, okay, your ping pong ball is actually at the crest, which means it has the maximum amplitude. It will have the maximum amplitude. And because it's at the crest, this amplitude is actually positive value. Okay, remember for transverse wave, we actually take upwards as positive and now downwards as actually negative. Okay, so when we talk about the crest, the ping pong ball is at the crest. Okay, it's at the crest. It will mean that it's at having a maximum amplitude and it's always a positive value. So you will know that at time 0 now, when the ping pong ball is at the center of the dark band, is what we known as aka known as the ping pong ball is at the crest. At the crest, it will mean that at the top, at time 0, it will have a maximum amplitude of positive A. Now, when it's at a positive A, okay, like we all know, all waves go through 4 cycles. Okay, so which means for a wave itself, okay, for a wave itself, let's say for a particle at the top, okay, he will go through 4 cycles, namely, he will go down to the equilibrium position. Then after that, he will transverse to the opposite end. Okay, then after the third part, he will go back to the equilibrium position again. After that, he will go up to back to his original maximum position. This is what we mean by the 4 cycle. So, or what we call your 1 period. So similarly, if your wave is happen to be at the center, okay, so you'll go through the 4 motion again. You either go up to the maximum position, come down again to the central, okay, to the central position, go down to the maximum on the opposite side. Then after that, you'll go back up to the original position again at the center. So every wave particles will actually go through 4 phases. We're going to clock your what we call your 1 cycle or your 1 period. So now if your wave is at the top now, if your wave is at the top, okay, so your wave now is at the top, okay, so it's currently at this position. So the next phase you're going to hit the equilibrium position. So which means that your wave will be back at the equilibrium position whereby the amplitude is actually 0. Okay, then now after that, your wave will go through the third phase. He will go down to the negative quadrant here. Okay, so he will go down to the negative side. Then repeat the motion again to the equilibrium and finally back to his original position. So you'll find that when the question tell you that it's at the center of that band, it means that it is actually at the top of the wave itself, what we know as the crest. And the final shape that you see, if you mark out all the wave itself, you'll find that you will get a nice cosine curve, okay, that clocks all the necessary points. And of course, based on the question say draw 2 cycles. So this is only 1 cycle. So this is 1 cycle. Okay, this is 1 cycle. So you have to plot another or draw another cycle that we look at. Okay, so this is a 2 cycle. Okay, so these are 2 cycles, and one of the important factors that you have is, remember at the beginning you found that the wave is actually period of 0.5 seconds. So which means your 1 cycle is actually your period, which means that this point is actually 0.5 seconds, and the second cycle here will be actually 1.0 seconds. Your wave will clock exactly, okay, or a cosine curve with a period of 0.5 seconds, and the amplitude is actually positive A and negative A respectively. Okay, so for this question, the important fact that the students have to resit is it comes in 2 parts. First part is that the students must know that the speed and the wavelength will give us one important information known as the period. And second thing that the student has to elicit is the information of the statement center of dark band. What does dark band, what does bright band means in terms of your wave location? So here, students have to take note is that for dark band, it means that it is the crest of the wave. Crest of the wave, because the crest of the wave, it has to actually travel a long or a big portion of the water, and when light travel through water, light actually get absorbed by the water, and as a result, by the time it hits the bottom, you actually have minimum energy, and as a result, it actually forms a dark band. And the reverse will be true for light ray coming from that hitting the trout. Okay, remember it has a small depth, a little depth of water, and the water depth only absorb a small portion of the solar energy or the light energy. And as a result, so most of the light energy actually hits the plate, and when it hits the bottom, you'll find that you see a bright band. Okay, so dark band correspond to crest, bright band correspond to trout. So once you get this, once you understand these 2 segments, you'll find that you will be able to draw the wave, the displacement time graph easily. Okay.
Part D here. Okay, part D. Okay. Now explain how energy is actually, part D, part 1, explain how energy is actually being converted. Okay, how energy is being transferred. Okay, like I mentioned before, how energy is transferred, how sound is produced, how I hear the sound, how sound is actually transmitted from position A to position B. All these questions actually have a similar technique that we actually employ. Whenever you see this type of question, it consists of two parts. The answer actually consists of two parts. The first part will actually be the definition of longitudinal wave. Then after that, the second part will actually require the student to invoke the transmission of wave particles, which means you will need to insert what we call a series of refraction and compression so that it can be sound is being transmitted. Okay, so you actually have two components in this answer. It's always the first component is always the definition of longitudinal wave. You tell me how the wave particle move with respect to the wave motion. Okay, in this case, it's parallel. Okay, the second portion of the answer will involve students telling me, denoting that how the wave is being transmitted, okay, through a series of refraction and compression. So I would say this set of answer is actually universal to different type of questions, and this type of question actually ranges from how sound is being transferred, how sound is transferred from point A to point B, how I hear sound, how sound is produced in a speaker, etc., etc. Whereas it all has the same, I would say, the format of answering. Now, part 2, okay, nail is dropped. Okay, now the nail is dropped. The sound produced is half the sound produced by the beam, half the sound. Okay, the loudness is produced. Then after the frequency is actually twice the beam. So when we talk about loudness, we are looking at amplitudes. We're looking at, So when we're looking at loudness, we are looking at amplitudes. And we are looking at frequency. And when we're looking at frequency, we are looking at pitch. Okay, so these two are related one. So when we say frequency or pitch is twice, okay, so it will mean the frequency is twice. It will mean that, okay, frequency is twice. It will mean that the period is actually half. Okay, and when you say amplitude is half, okay, loudness is half, it will mean the amplitude is actually half. Okay, so which means all in all, this particular graph in 11.4 actually will shrink. Okay, so which means I need the periods to be half. Okay, amplitudes to be half. So amplitude to be half, the wave will be here. One cycle used to be here. Now my cycle is here. Okay, so the wave will look something like this. Okay, so this will be half A, negative half A. Okay, so this is what we mean by the amplitude is half, or what we call the loudness is half, the frequency double, or what we call the pitch is double, or sometimes we call this the period is half. Okay, so it's just some representation or a representation of your loudness and pitch in terms of the respective components known as your amplitude and frequency. Okay, now with this, okay, this will be the end of the paper 2. Okay, we have come to the end of the paper 2. Okay, if you need the paper 1, I'll leave the link in the top right hand corner so that you can access it. Okay, I hope this 1 hour has been meaningful for you and been useful for you. Okay, I hope it has actually helped to clear out some of your doubts. And if you need any explanation, or if I've explained anything wrongly, feel free to feedback to me and leave your comments at the bottom so that I can get back to you ASAP, or can update the video with the necessary corrections. Okay, and last thing is that I do hope the videos that I will be uploading, I have uploaded previously and I will be uploading in the future, actually helps ease up your stress load in learning physics, in picking up physics, okay, and maybe increase your passion by a bit in learning physics. Okay, if not, okay, this is where I end off. Okay, all the best, okay, to your exam, okay, for everybody. Okay, see you.